Hello everyone and welcome to another episode on this video channel. In today's lesson, we want to learn how we can verify to see if a function is a solution to a given PDE. We want to learn how we can verify to see if a function is a solution to a given PDE. This is what we want to learn in this video lesson. If you haven't subscribed to the channel, kindly hit on the subscribe button for me. So to verify to see if this function is a solution to this PDE, then it means that this function satisfies this PDE. So in verifying, what we are going to do is to take the first partial derivative of the function with respect to x, then we take the third partial derivative of the function u with respect to x, and then we substitute them into this equation. Once we are done, then we compare to see if what is on the left hand side is equal to what is on the right hand side. That is all what we have to do, or that is all what we are going to do in today's lesson. So without wasting my time, let's look at this example. We want to verify that the function sine x is a solution to this PDE. So first, we have to find the first partial derivative of the function with respect to x. So we have our ux. So our function is sine x. And whenever we differentiate sine x, what do we get? We get cos x. Very, very easy. So we are done with this. Let's continue with this. So we look at the second partial derivative of the function with respect to x. Now, when we differentiate cos x, what do we get? We get negative sine x. Then look at the third partial derivative of the function with respect to what? X. So when we differentiate sine x again, what do we get? We get what? Cos x. So once you have all of these derivatives, we substitute them into the PDE that was given. So we have ux, our ux is what? Cos x. We have ux plus what? Ux x is equal to 0. So our ux, we had cos x, so we have cos x, then we have plus uxs, we had negative what? Cos x is equal to what? 0. So we have cos x minus cos x is equal to 0. So cos x minus cos x will give us what? 0. And this is the same as what is on the right hand side. So you can therefore say that this function is a solution to the given PDE because it satisfies the PDE. What is on the left hand side is equal to what is on the right hand side. Very, very easy and then simple. So we want to show that this function sine xy is a solution to the PDE. This is the PDE. We want to verify if this is a solution to the PDE. So with that, we are going to follow the same approach here. We are going to follow the same concept. So first, we are going to take the second partial derivative of this function with respect to x. Then we take the second partial derivative of the function with respect to y. So let's start with this. So we have ux, that is the first partial derivative of this function with respect to what? Sine xy. So with this, we are going to apply the chain rule. We differentiate outside, then we multiply it by the derivative of the inside function with respect to x. So when we differentiate sine xy, we are going to get what? Cos xy, then we multiply it by the derivative of the inside function. We are differentiating with respect to x, so y becomes a constant. Then we differentiate x with respect to x, we get what? 1. So we multiply it by that. So we are going to get ux is equal to y cos x what? Y. Then we take the second partial derivative of the function with respect to what? X again. So we can still apply the product rule. We can use the product rule to find this. But since we are differentiating with respect to y, so we take the second partial derivative with respect to what? X. So we can apply the product rule. But since we are taking the partial derivative of this function with respect to x, y becomes a constant. So we have y, then we differentiate this with respect to what? X. So we differentiate the outside, we differentiate the inside. When we differentiate cos x, we are getting what? Minus sine xy. Then we multiply it by the derivative of the inside function with respect to x. So we have del x of the inside function xy. Since we are differentiating with respect to x, y becomes what? A constant. Then we differentiate x with respect to x, we have 1. We have y, sorry. So we have our second derivative with respect to x. Y times y will give us what? Y squared. We have minus y squared sine xy. Now that we are done with the second derivative with respect to x, we move on to the second partial derivative with respect to y. So we have uy. When we differentiate sine xy, we are going to get what? Cos xy. Then we differentiate the inside function, that's the chain rule, with respect to what? Y. So x becomes constant, and then we differentiate y with respect to y, that is giving us what? 1. X times 1 will give us what? X. So you multiply it by that. Then we take the second partial derivative of the function with respect to what? Y. So since we are differentiating with respect to y, x becomes constant. So we are going to repeat it. Then we differentiate this with respect to what? Y. So when we differentiate cos xy, we are getting negative sine xy. Then we differentiate the inside the y of the inside function. We are going to get what? X, because x becomes constant. Then we differentiate y with respect to y, we have 1. So we have multiplied by what? X. X times x will give us x squared. So we have minus x squared sine xy. So once we have this second partial derivative of the function u with respect to x and y, we substitute them back into the PDE that was given. So let's start from here. So we have x squared. Our uss, we had this. So we have minus y squared sine xy. Then we have minus y squared. Uyy, we had this. So we have minus x squared sine xy should be equal to what? 0. So we are going to check if what is on the left hand side will give us 0. If it gives us 0, then we can say that this function is a solution to the PDE up there. So from here, we can see that this and that will give us minus x squared y squared sine xy. And again will give us 4. We have x squared y squared sine xy is equal to 0. So we have minus x squared y squared sine xy plus x squared y squared sine x squared. So you can see that this and that will give us 0, and that is equal to what? 0. So you can see that what is on the left hand side is equal to what is on the right hand side. So you can therefore say that the function sine xy is a solution to this PDE. Very, very easy and then simple. Let's look at these two particular examples. So let's start with this one. We want to verify that the function xy ln x is a solution to this PDE. So we are going to apply the same concept, the earlier concept that we used. We are first going to take the partial derivative of the third partial derivative of the function u with respect to what? X and then y. So we have our us as the first partial derivative of the function u. So we have xy ln x. So we have xy ln what? X. Since we are taking the partial derivative with respect to what? X, the function y becomes a constant, so we can write it or we can keep it. Then we'll be left with what? X ln x. So we have x ln what? x. So with this, we have two functions and they are multiplying. So we can apply the product rule, which says that we keep the first function, we differentiate this, plus we keep the second function, we differentiate the first function. I believe you remember that. So that's what we are going to apply here. So we are going to keep the first function. Let's continue from down here. So we are going to keep the first function, which is x. Then we differentiate the second function, ln x, with respect to x. And that's going to give us what? 1 over x. Then what we do again, we keep the second function, ln x. Then we differentiate x with respect to x. That is giving us what? 1. So you can see that this x, we cancel this x. We are left with what? Y times 1 will give us what? Y. Plus y times ln x will give us what? Y ln what? X. So it means that when we take the partial derivative of this function with respect to x, we are getting what? Y plus y ln what? X. Then we take the second partial derivative of that function with respect to what? X again. So we have this del x of this function y plus y ln what? X. Since we are differentiating with respect to x, y here becomes what? A constant. And whenever we differentiate a constant, what do you get? We are going to have dx of the constant 2. When we differentiate 2, we get what? 0. We are differentiating 2 with respect to x, so we are going to get 0. So the same thing applies to that. The same concept applies to this. The y is treated as a constant because we are differentiating with respect to what? X. So this is going to give us 0. And then this y is multiplying what? Ln x. So we have two functions. So this y here becomes a constant. So we keep the constant. Then we differentiate ln x with respect to x. That's going to give us what? 1 all over x. So at the end, we are having what? Y all over x. Very, very easy. So when we differentiate the whole of this function with respect to x, we are getting y all over x. Then we take the third one with respect to what? Y. So we have u, x, and then y. So we have del what? Y. With this one, we are differentiating with respect to y of the function y all over x. Remember that y all over x, we can write it as y multiply 1 over what? X. You agree with me? Good. If that is the case, then I'm going to write it in that particular form. I'm going to write it as y multiplying 1 over x. Since we are differentiating with respect to y, 1 over x becomes what? A constant. So we have 1 over x. Then we differentiate y with respect to y. We are getting what? 1. So del the y of the function y over x is equal to what? 1 over x. So we have here to be 1 all over x. Now once we are done with this part, we move on to the second partial derivative of the function with respect to what? Y. So we have uy, that is the first partial derivative of this function with respect to y. So let's come here. Del what? Y of the function xy ln what? X. Since we are differentiating with respect to y, the function x ln x becomes constant. So we have x ln x becomes constant. Then we differentiate y with respect to y. That is giving us what? 1. So we are left with x ln x. X ln what? X. Then we differentiate again with respect to what? Y. We are differentiating the function x ln x with respect to y. Now the whole of this is treated as a constant. So when we differentiate a constant, what do we get? We get 0. So the second partial derivative of this function with respect to y, we are getting what? 0. So once we have this, we substitute them into the PDE that was given. So we have, where is it? U. Our U is what? Our U is the function. So U is given as this. So we are going to write it x, y, then what? X, and then multiply by what? U, x, s, y. U, x, s, y, we had 1 all over what? X. Then we have plus our x. Then we have u, y, y, we had 0. So multiply by 0 is equal to what? Y, then what? X. So we are going to check to see if what is on the left hand side here will give us y ln x. If it does, then we can say that the function x, y ln x is a solution to the PDE that was what given. Very, very interesting. So for me, we can see that this is, we cancel one of the x here. We are left with y ln what? X. This is going to give us 0. And then we have y ln what? X. So you can see that what is on the left hand side is equal to what is on the right hand side. So therefore, we can say that the function x, y ln x is a solution to this PDE. As easy as that. And then case closed. Let's look at this, the last one, and then we vamoose. So we want to look at the function, this exponential function. We want to check to see if it is a solution to this PDE. Following the same concept, we are going to take the second partial derivative of this exponential function with respect to x, and then with respect to xy, and then x. So let's start with respect to x. How do we differentiate an exponential function? So to differentiate an exponential function, let's say dx of what? E exponent what? X of x. Let's take x for the start. So to differentiate an exponential function, what do? We keep the function, then we differentiate the exponents with respect to x. So when we differentiate the exponent is what? X. So we have dx of what? X. That's going to give us what? 1. So multiply by 1. So we have e exponent x. So in differentiating an exponential function, we repeat the function, then we multiply it by the derivative of the exponent, and then you are good to go. Apply the same concept here. We are going to repeat the function. So the function is what? E exponent xy. Then we multiply it by the derivative of the exponent with respect to x. So we have the what? X of the exponent, which is what? Xy. We are taking the partial derivative of the exponent with respect to x. So with that, let's continue. We have ux is equal to e exponent xy multiplied by, since we are differentiating with respect to x, y becomes what? A constant. And when we differentiate x with respect to x, we get 1. And then case closed. So we can write this as ux is equal to y e exponent what? Xy. Then we take the second partial derivative of that with respect to what? X again. Since we are differentiating with respect to x, y becomes a constant. We can still apply the product rule. Y becomes a constant, and then we differentiate what? E exponent xy with respect to x. So we are going to repeat the function, then we differentiate the exponent xy with respect to x. So we are going to get what? Y. So we have our u x is equal to y times y will give us what? Y squared e exponent what? Y. Then we are done with this, so we move on to this. So we are going, let's continue from this side. So remember that when we were looking at the order of derivative, we said that if the function is a continuous function, the order of taking the derivative doesn't matter. So when you have u, x, y, x, somebody can decide to take the derivative in this order, u, x, y. At the end of it, or this will be the same as that. the order of taking derivative in differential calculus doesn't matter if the function is a continuous function. So I would prefer taking it in this order. So we are going to continue from here. E exponent xy, we are differentiating it with respect to what? Y. So it means that we are to apply the product rule. Since we are differentiating, let me write the function here. Y squared E exponent xy. This is a function of y, this is a function of x and y. So we are going to treat this as a product rule. So we keep the first function, we differentiate the second function, then we continue from there. So we have u x x y. So we keep the first function, which is what? Y squared. Then we differentiate e exponent xy with respect to y. So we are going to get e exponent y. Then we have what? X. Then we have plus. So the first one we kept what? Y squared. So the second part we are going to keep what? E exponent xy. The product rule. So we have e exponent xy. Then we differentiate what? Y squared with respect to y. That's going to give us what? 2y. We have 2y. So we have u x x y is equal to, this is going to give us x y squared e exponent x y plus 2y e exponent what? X y. So we are done. So once we have this, which is this, and then this, which is this, we just substitute them into the PDE that was given, and then we are good to go. We are going. Heaven knows where we are going. We know we will. So the PDE that was given is uxx plus uxyx is equal to y squared 1 plus x multiplying u. Y squared e exponent xy. Then we have plus our uxyx. We had x y squared e exponent xy plus what? 2y e exponent xy is equal to y squared 1 plus x. Our u is given as what? E exponent xy. So let's write it e exponent y. So what we are going to do is we are going to expand this and then we compare the term to see if some can cancel some. So we have y squared e exponent xy plus xy squared e exponent what? Xy plus 2y e exponent xy. When we expand this, we are going to get this, and that. We are going to get y squared e exponent xy plus this, and that. We have x y squared e exponent what? Xy. So you can see that we have y squared e exponent y squared e exponent xy. This and that will go. We also have this and that will go. So at the end, we are left with what? 2y e exponent xy. This part is equal to 0. So you can see that what is on the left hand side is not equal to what is on the right hand side. So you can say that the function u, which is e exponent xy, is not a solution to the PDE that was given. Very easy and then simple. This brings us to the end of today's lesson. See you tomorrow. Bye.